Before America replaced it, you could hear this engine coming from blocks away. A hard metallic bark. A rising mechanical scream. A city bus leaving the curb. A truck climbing a grade. A fishing boat pushing into weather. The strange part is that the sound belonged to the same basic engine family that had already gone to war. In one form, 2 of its 6-cylinder units were coupled together inside the M4A2 Sherman. In another, 8 of them drove a landing craft toward a beach. Then peace came, and the same architecture went to work in ordinary America. It was called the Series 71. The number did not describe horsepower. It described a promise, 71 cubic inches per cylinder, repeated as many times as the job demanded. For decades, that promise made Detroit diesel almost impossible to avoid. Then the highway market changed its mind. So what happened to Detroit diesel? And how did a compact 2-stroke become one of the hidden mechanical standards inside working America? Detroit's story begins in 1938, when General Motors formed the GM Diesel division. The official company timeline says the new division produced the 2-cycle Series 71 for construction, military, and standby generator use. That list matters. This was not conceived as a single-purpose truck engine. It was conceived as a family of power units that could move between jobs. The organizing idea was brutally simple. Each cylinder displaced roughly 71 cubic inches. Add cylinders, and the engine grew without abandoning its basic logic. A 2 to 71, 3 to 71, 4 to 71, and 6 to 71 could share a recognizable design language. Later V configurations extended the family into 6V, 8V, 12V, and 16V forms. The exact components were not universally interchangeable across every generation and layout, but the modular idea reduced the number of completely different engines that operators had to understand. That was especially valuable in the late 1930s. America was building roads, industrial plants, ships, and electrical systems, but the country did not yet know how much machinery it would soon need, or where it would be needed. A standardized engine family offered something more useful than a spectacular peak number. It offered repeatability. Open the 1939 operating manual preserved by the Henry Ford, and the Series 71 appears not as nostalgia but as a working system. Lubrication, cooling, fuel, air, starting procedure, and maintenance are treated as parts of one disciplined routine. The manual is evidence of what industrial power really requires. An engine is useful only when an operator can start it, a mechanic can diagnose it, and a supply chain can keep it alive. The manual also reveals an industrial idea that is easy to miss when an engine is displayed behind a rope. Knowledge had to be portable. A mechanic in a municipal garage, a shipyard, a construction camp, or a military workshop could not depend on the engineer who designed the machine standing nearby. Clear procedures turned factory knowledge into field capability. Specifications, adjustment sequences, inspection points, and troubleshooting logic allowed organizations separated by thousands of miles to perform recognizable work on the same family. That transfer of knowledge was as important as the casting itself. That is the first reason the Series 71 mattered. America did not merely need engines. It needed engines that thousands of ordinary organizations could learn to use. But the mechanical trick that made the engine compact also gave it the sound, and eventually some of the limitations, that would define its reputation. A 4-stroke diesel needs 4 piston strokes to complete its cycle: intake, compression, power, and exhaust. The Series 71 completes a power cycle in 1 crankshaft revolution. Every downward power stroke is followed by scavenging and compression in rapid succession. In theory, that gives a 2-stroke excellent power density. In practice, it demands careful control of air. Near the bottom of the cylinder, the descending piston uncovers intake ports in the liner. Pressurized air enters through those ports. Exhaust leaves through valves in the cylinder head. The incoming air must sweep, or scavenge, the burned gases out before the piston closes the ports and compression begins again. That is why the familiar Roots-type blower is not an optional performance accessory on a naturally aspirated Detroit 2-stroke. It is part of the breathing process. Without forced scavenging air, the engine cannot clear the cylinder properly. Later turbocharged versions could add more air and power, but the blower remained integral to low-speed operation and scavenging. This arrangement made the engine compact for its output. It also made it busy. Blower rotors turn. Camshafts operate exhaust valves and mechanical unit injectors. Each injector meters and pressurizes fuel at the cylinder. At high speed, combustion events arrive twice as often per crank revolution as they do in a four-stroke. The result is the fast, hard-edged exhaust note that enthusiasts nicknamed the "Screamin' Jimmy." The sound was a consequence, not the purpose. The purpose was to place dependable diesel power where a larger, slower engine would be awkward. The narrow inline 6-71 could fit under a bus floor, behind a coach, inside a boat, beside generator equipment, or in a military installation. The same core geometry could be tuned for different ratings and duty cycles. But power density always sends a bill. Airflow, cooling, lubrication, injector setting, and governor adjustment had to remain correct. A two-stroke that was poorly maintained could smoke, leak, run away, or turn its famous sound into evidence of abuse. The machine rewarded mechanics who understood it and punished organizations that treated familiarity as immunity. This is where the Series 71 became more than a clever design. It created a body of shared knowledge. Mechanics learned the blower. Fleets learned the injectors. Parts counters learned the family. Training material, tooling, rebuild practices, and field experience accumulated around the architecture. Then war turned that accumulated logic into national capacity. World War II did not reward machines that were merely elegant. It rewarded machines that could be produced in volume, adapted quickly, shipped far from the factory, and repaired by people working under terrible conditions. Detroit says that in 1943, a workforce of 4,300 produced 57,892 Series 71 engines. That number is a manufacturer claim, but even with that qualification it reveals the scale of the mobilization, more than 57,000 engines from one family in a single year. Volume alone was not the whole advantage. Wartime production had to survive interruption. Engines arrived in different vehicles, climates, and commands. Crews changed. Workshops improvised. A design family became strategically useful when a replacement unit, a trained mechanic, a familiar adjustment, or a known failure pattern could move across that disorder. The Series 71 did not eliminate the complexity of war. It concentrated part of that complexity into a machine already supported by drawings, fixtures, suppliers, and accumulated repair knowledge. That meant the industrial system could spend less time inventing a new answer for every installation and more time reproducing an answer it had learned to trust. The M4A2 Sherman provides one of the clearest examples of adaptation. Its GM 6046 powerplant coupled two 6-71 engines into one package. The result was not the powerplant used in every Sherman, it belonged specifically to the M4A2 variant. But it demonstrated the strategic advantage of an existing industrial engine. Rather than wait for an entirely new diesel to mature, engineers could combine proven units and put them into production. At sea, the multiplication became even more literal. The historic American engineering record for LCI, L. 653 describes 8 General Motors 6-cylinder Series 71 engines, installed in groups of 4 for each of 2 propeller shafts. 8 engines in one landing craft sounds mechanically excessive. Yet it also offered a wartime answer to urgency: assemble the required power from units already available, already understood, and already moving through the production system. That landing craft carried infantry toward shore. The engines were not symbols to the people aboard. They were one link in a chain that included steel, fuel, propellers, maintenance, navigation, and human judgment. If any link failed, the beach was still far away. The Series 71 also served in generators, construction machinery, and other military equipment. Those roles are less cinematic than a tank or landing craft, but they may be more revealing. Armies do not move only by fighting vehicles. They move by road graders, pumps, cranes, workshops, lights, and power. A modular diesel family could disappear inside all of those systems. This was one of America's great wartime advantages, not one perfect machine, but an industrial ecology capable of repeating useful designs. A cylinder, an injector, a blower, a manual, a mechanic, a production fixture, each could be copied, taught, and distributed. When the war ended, that ecology did not vanish. It came home looking for civilian work. The post-war United States expanded outward. Suburbs grew. Highways lengthened. Cities needed transit. Construction pushed across new land. Freight moved farther and more predictably. The Series 71 entered this world with two advantages: it already existed at scale, and thousands of mechanics already recognized its logic. Detroit's own history says the Series 53 arrived in 1957 for the expanding on-highway market, and that the Series 71 was soon made widely available to heavy-duty trucking. The important point is not that the 71 arrived alone. Detroit built a family of two-strokes that let fleets select an engine around the vehicle and the job. In transit buses and intercity coaches, packaging mattered. A bus has to reserve most of its volume for passengers. A compact diesel installed beneath the floor or at the rear turned mechanical density into revenue space. Its acceleration did not need to be glamorous. It needed to happen hundreds of times a day, from curb to traffic, carrying workers, students, shoppers, and families through the routines of a city. For a transit operator, the engine was only one component of a public promise. A route printed on a timetable assumed that vehicles would leave the depot, survive repeated stops, return for inspection, and be ready again for the next shift. Standardized fleet knowledge connected those cycles. Mechanics could compare one bus with another. Supervisors could plan spares. Parts departments could stock around recurring work instead of treating every failure as a unique emergency. The national consequence was not merely more horsepower. It was the ability of local organizations to turn mechanical repetition into dependable service. In trucks, the Detroit two-stroke developed a different reputation. Drivers learned to keep it in its power band. The engine liked revolutions. On a grade, a driver could not always lug it like a large low-speed four-stroke. The sound rose, the tachometer stayed busy, and the truck continued uphill. That driving style became part of the machine's folklore. On construction sites, in mines, and beside industrial equipment, the Series 71 offered a common answer to uncommon problems. A pump did not look like a crane. A generator did not look like a loader. But if their engines shared service principles and parts channels, an operator could support a wider set of machines without building a separate mechanical culture for each one. This is the second transformation in the story. Wartime production had proven that the engine family could be multiplied. Post-war America proved that it could be dispersed. The Series 71 moved people who never knew its name. It moved freight that never carried its badge. It powered work far from Detroit. In doing so, the engine became a standard hidden inside other standards: bus schedules, delivery routes, road projects, utility plans, and fleet maintenance cycles. And on the water, where replacement is expensive and reliability has a different emotional weight, the same architecture found another long life. A marine engine earns trust differently from a showpiece. It has to start when the dock is behind you. It has to work at a steady load. It has to tolerate salt, vibration, cramped access, and long periods when the nearest parts counter is far away. The Library of Congress record for the fishing vessel Shenandoah lists a Detroit diesel 12V71, 12 cylinders, 300 horsepower, 1,800 revolutions per minute, keel-cooled, driving a 5-blade bronze propeller through reduction gear. That is not a brochure claim. It is a documented working installation inside a salmon purse seiner. The details reveal why marine operators valued the family. The propeller did not care about the engine's mythology. It cared about torque delivered through gearing, cooling maintained under load, fuel available on board, and a crew able to keep the machinery running. The Series 71 fit into that practical world because it was already supported by decades of knowledge. Marine versions also demonstrate the limits of telling this story as a straight rise and fall. On the highway, a new engine can enter through fleet turnover and regulation. On the water, vessels may remain in service for generations. Repowering a boat is not simply buying an engine, it can involve foundations, shafts, cooling, exhaust, weight distribution, controls, and certification. The installed system creates inertia. That inertia can preserve old machinery long after its original market has changed. It is not always irrational. If parts remain available, mechanics retain knowledge, and the engine still matches the duty, rebuilding can be less disruptive than redesigning the vessel around a new power plant. But age also creates risk: worn components, disappearing specialists, uncertain histories, and engines assembled from decades of revisions. Survival is not proof that every old engine is safe or economical. The same logic appears in standby generators and industrial plants. A machine that runs only when the grid fails may accumulate hours slowly. Its owner may value known starting behavior and existing maintenance more than a small efficiency gain. The Series 71 could therefore remain useful in corners of the economy even as it became uncompetitive in new highway vehicles. That distinction matters. Detroit Diesel did not wake up one morning and discover that the engine had stopped working. The system around the engine changed what working meant. By the 1970s and 1980s, heavy-duty diesel design faced a new combination of pressures. Fuel cost mattered more. Fleets demanded better economy. Emission standards tightened. Diagnostics and electronic control became more valuable. The old Detroit two-stroke could be improved, turbocharged, and refined, but its architecture had been created for a different selection environment. A two-stroke scavenging process must move fresh air through ports while exhaust is leaving the cylinder. That overlap makes airflow management fundamental. Mechanical unit injectors can meter fuel precisely for their era, but a fully electronic system can respond more flexibly to speed, load, temperature, timing, and emissions requirements. As standards tightened, the question was no longer only whether an engine could make power reliably. It was whether it could make that power while meeting a shrinking envelope for fuel consumption and pollutants across a regulated test cycle. Detroit's answer was not to perfect the Series 71 forever. In 1987, the company introduced the four-stroke Series 60. Detroit describes it as the first production heavy-duty diesel to use integrated electronic controls as standard. The engine combined four-stroke breathing, electronic management, and a design aimed at fuel efficiency and the modern Class 8 market. This is the crucial conflict. The Series 60 was a Detroit engine too. The company that built its identity on two-strokes became the company that replaced them. EPA's heavy-duty market analysis makes the transition unusually clear. In 1996, the agency wrote that Detroit had decided to replace the 6-71 and 6-92 two-strokes with the Series 50 and Series 64 strokes. The document said the two-strokes were still offered in 1996 but were expected to phase out over the next 2 years, with remaining sales in buses and selected truck models designed around them. The change also moved expertise inside the vehicle. On a mechanical Detroit, a skilled technician listened, measured, adjusted linkages, set injectors, and interpreted smoke, temperature, and response. Those abilities did not become worthless, but electronic control added another layer: sensors, fault codes, software logic, and data shared across the powertrain. A modern fleet could ask not only whether the engine was running, but what it had recorded before a fault appeared. That changed training, tools, inventory, and the relationship between the engine maker and the vehicle operator. Replacing the two-stroke was therefore not a single engine swap. It was a migration from one maintenance culture to another. That is not a story of government acting alone, and it is not a story of management acting alone. Regulation changed the acceptable emissions envelope. Fuel economics changed fleet priorities. Electronics changed what operators expected from control and diagnostics. Competitors changed the performance benchmark. Detroit responded with a new architecture. The old two-stroke lost the new highway market because continuity was no longer the strongest advantage. A familiar mechanic and a stocked parts room still had value. But they could not indefinitely outweigh the compound benefit of better fuel economy, cleaner operation, electronic optimization, and compliance headroom. America had not stopped needing diesel power. It had changed the test that diesel power had to pass. The easy title for this story would be The Rise and Fall of Detroit Diesel. It would also be wrong. The Series 71 faded from new on-highway production, but Detroit did not disappear. The company reorganized, separated from older General Motors structures, expanded the four-stroke line, and ultimately became part of the Daimler commercial vehicle system. The modern Detroit brand sells engines, transmissions, axles, connected services, and powertrain technology built around a world very different from 1938. What ended was not the company. What ended was the two-strokes position as Detroit's forward-looking highway standard. That change created two Detroits in public memory. One is the modern manufacturer, electronically controlled, emissions compliant, integrated into the truck as a networked powertrain. The other is the mechanical memory, oil-stained valve covers, unit injectors, roots blowers, and an exhaust note that can still pull a crowd at a truck show. Nostalgia can confuse those two stories. Enthusiasts may hear the sound and remember durability. Fleet managers may remember fuel consumption, leaks, smoke, or the work required to keep an aging engine compliant. Both memories can be true because they measure different things. A machine can be beloved and obsolete in one market. It can be inefficient by new standards and still economically rational in a legacy installation. The continuing parts, rebuild, marine, military, and collector ecosystem shows how deeply the architecture was installed. But survival should not be exaggerated into dominance. A rebuilt 6-71 in a boat does not mean the design could return to a new highway truck unchanged. It means the old system still contains places where old knowledge retains value. That is what happened to Detroit Diesel. The brand moved forward by leaving its most famous architecture behind. And that answer leads to a larger question. What did America gain from the Series 71 before it moved on? The greatness of the Series 71 was not that it was perfect. It leaked. It demanded air. It rewarded skilled adjustment. It eventually lost the efficiency and emissions contest in new highway service. Its greatness was that America could repeat it. One-cylinder logic could become multiple engine sizes. One service culture could reach buses, trucks, boats, generators, and military machines. One production system could expand in wartime and disperse in peace. Manuals, parts, mechanics, and rebuilders could travel with the engine into places the factory would never see. That repeatability converted mechanical design into national capability. A bus route became more dependable because a fleet knew its engines. A landing craft became possible because power could be assembled from proven units. A fishing vessel stayed productive because an installed engine could be rebuilt. A generator stood ready because someone knew how to make it start. Industrial resilience often looks like surplus knowledge. It is the retired mechanic who recognizes a sound before a gauge moves. It is the manual still legible on a workbench. It is the supplier able to identify a part from a casting number, and the training shop where the next mechanic learns why a procedure exists. None of those things appears on an engine's horsepower rating. Together, they determine whether machinery remains useful when a schedule tightens, a storm closes the road, a vessel is far from port, or a power failure turns a standby generator into essential infrastructure. The Series 71 accumulated that surrounding capability over decades. This is how machinery helps make a country powerful. Not by appearing in a museum, but by becoming ordinary. The most important engine may be the one hidden behind the timetable, the construction schedule, the cargo manifest, or the switch marked emergency power. The Series 71 also leaves a warning. Standards create capacity, but they create inertia. The more knowledge, tooling, and equipment a society builds around one architecture, the harder it becomes to replace. Eventually the cost of continuity can exceed its benefit. When that moment comes, a company has to decide whether it is loyal to the machine, or loyal to the work the machine was created to do. Detroit chose the work. The four-stroke Series 60 replaced the two-stroke on the highway. Electronics replaced much of the old mechanical control. New standards redefined acceptable exhaust. The company survived because it changed the engine before the market changed the company. But the old sound did not disappear completely. Somewhere, a 6-71 still turns a propeller. An 8V71 still waits behind a generator panel. A restored coach still pulls away from the curb. The exhaust rises, the blower turns, and 71 cubic inches per cylinder goes back to work. Not because America failed to move on. Because, for a long time, This was one of the machines that taught America how to keep moving.